Okay, let's look at the next problem where we need to deal with one trigonometric function. So the derivative has been computed, so we could simply use it. Okay, so let's start from its domain. So sine of x is defined everywhere, cosine of x is defined everywhere, so there's no trouble from these two trig functions. Okay, but also notice that this guy is in the denominator, so we need to make sure that this guy is never zero. So 2 plus cosine of x equals to 0 means cosine of x equals to minus 2, so no solution. So therefore, the domain is simply going to be minus infinity to cos infinity because there's really no restrictions on the function f. And now let's look into the y-intercept and x-intercept. For the y-intercept, we simply plug in x equals to 0. So this will be sine of 0 divided by 2 plus cosine of 0. So this will be 0 divided by 3 plus 1, and the answer will be 0. So this is the y-intercept. Okay, so the x-intercept will be much more complicated. So you see that to make f of x equals to 0, so this means sine of x has to be equals to 0. And then we will get a huge number of x-intercepts. So x is going to be equals to k pi, where k equals to 0 plus or minus 1 plus or minus 2, etc. So basically speaking, we have got infinitely many x-intercepts. Okay, should we be worried about it too much? Well, sometimes you probably have to, but for this problem, as you will see from the next step, when we try to determine the symmetry, you see that it's really not that much to worry about. So first, if you look at the f of minus x, you will see that this is going to be sine of minus x divided by 2 plus cosine of minus x. So sine of minus x is equals to minus sine of x, and cosine of minus x is simply going to be 2 plus cosine x. All right, so this is what I have, and I know that this is precisely minus f of x, so this means it's odd function. Okay, so this allows us to focus on 0 to infinity, but actually we can do much better than that. We will be able to see that indeed f of x plus 2 pi, so this is going to be equals to sine of x plus 2 pi divided by 2 plus cosine of x plus 2 pi, but because of both sine x and cosine x are periodic functions, so, well, I will get sine of x plus 2 pi, and cosine of x plus 2 pi is simply going to be sine of x and cosine of x respectively. So this is going to be f of x. So this is telling me that it's 2 pi periodic. Okay, so if you really want to maximize the symmetry over here, so you should be able to tell that all you need to do is to focus on the interval. So these two combined together will simply tells you that you can simply focus on the interval minus 0 to pi. And why is that? Well, because you see that, so this is 2 pi periodic. So all I need to do is to focus on any interval that's going to be of 2 pi's length. And if I choose the interval to be minus pi to pi, if I choose the interval to be minus pi to pi, then, well, from the fact that we have got an odd function, all we need to do is to focus on half of this interval. So these two conditions basically tells you that you can simply focus on half of the period, namely 0 to pi. But let's not do this over here. Let's actually still focus on 0 to 2 pi. So pretending that we do not really know the function is odd function. So yeah, because I think this is so this makes the problem a little bit more complicated. So I will just focus on 0 to 2 pi instead of minus 0 to pi. This makes the problem a little bit more complicated. So I'm working on this slightly more complicated case simply to hope that you can get used to such level of complexity. Okay, so let's just focus on 0 to 2 pi. Okay, so let's look at the asymptote. So since we are focusing on a finite interval, so the horizontal asymptote is not applicable in this situation. And for vertical asymptote, because the function is defined everywhere, so we can conclude that there's no vertical asymptote. So this part is done. Now let's look at the derivative. So, well, if we let f prime of x equals to 0, so this means 1 plus 2 cosine of x equals to 0. So this will tell me that cosine of x equals to minus 1/2. Okay, so when x ranges between 0 to 2 pi, you should recognize that there are two values for you to take cosine x equals to minus 1/2. So this will be x equals to 2 pi over 3 and x equals to 4 pi over 3. So these are the 2 points where f prime of x equals to 0. Okay, so f prime of x does not exist, means the denominator 2 plus cosine x equals to 0. So this guy, we have seen that no solution. Okay, so these two numbers are the only critical numbers I have, and these two numbers separates the finite interval 0 to 2 pi over here. So this will separate it into 3 parts. So this is 0 and this is 2 pi. And I will have the 2 pi over 3 is over here, and then 4 pi over 3 is roughly over here. So I need to determine the sign of the derivative on these 3 intervals. Okay, so the procedure is the same. So we just need to analyze each factor. So I have got 1 plus 2 cosine of x, and I have another factor to be the square of 2 plus cosine x. So the second factor is pretty easy. So this guy is always positive on these intervals. So to determine the sign of the first factor, certainly you can use the graph of cosine of x as I did in the pre-lecture video, but I would like to do a little bit differently here. I would simply test the special values. Okay, so in the first interval, I can compute that 1 plus 2 cosine of pi over 2 is greater than 0, because this is going to be equals to 1 plus 0, that will be 1. So this is strictly positive, so that way I note my sign of the first factor will be positive here. Okay, so for the second interval, I can simply test the number pi. So 1 plus 2 cosine pi. So this will be minus 1, because cosine pi equals to minus 1. So what I get is 1 minus 2, and this is going to be negative. So this way I see that the factor takes negative values over the second interval. So for the last interval, I can simply test 1 plus 2 cosine of 3 pi over 2, and this is going to be 1 plus 0 again, so this will be 1. All right, so this way I get this guy is positive. So this is how I test the sign of the first factor using special numbers. You can certainly do it by yourself using the graph of the cosine function. Okay, so with this in mind, so we get the derivative is going to be positive, negative, and positive on these 3 intervals. Okay, so this tells me that my function value at 2 pi over 3, so f of 2 pi over 3. So let's first compute what this guy is. So this will be sine of 2 pi over 3 divided by 2 plus cosine of 2 pi over 3. Sine of 2 pi over 3 is going to be root 3 over 2. Cosine of that guy is going to be minus 1/2. Okay, so what I will get here is going to be root 3 over 2 divided by 3 over 2, and the answer will be root 3 over 3. So I know that my function value at 2 pi over 3. So this is local max by first derivative test. Okay, so similarly, we can compute f of 4 pi over 3. So this will be sine of 4 pi over 3 divided by 2 plus cosine of 4 pi over 3. Okay, sine of 4 pi over 3, this guy is going to be minus root 3 over 2. And cosine of 4 pi over 3, so this is still going to be minus 1/2. So this will be 2 minus 1/2. So then you do the arithmetic by yourself, the answer will be minus root 3 over 3. So that I know that f of 4 pi over 3 equals to minus root 3 over 3. So this is going to be a local minimum. Okay, so this finishes the part for part A. And I think I also need to know that f of 0 equals to 0 over here, and f of 2 pi, because this is going to be a periodic function, so I will keep the numbers over here. So these will be important when we try to sketch the graph. So I will just keep the function values over here. Now let's look into the concavity. So I will just copy f double prime here. So f double prime of x will be 2 sine of x cosine of x plus 1 divided by a cosine x minus 1. So then divided by 2 plus cosine x squared. So is this a square or cube? Probably doesn't matter. Okay, it's square. Wait a minute, is it correct? Nope, it's not. So I think the problem statement is a little bit wrong. So this should really be the cube. So it should be the third power of 2 plus cosine x in the denominator. Okay, so fortunately we discussed over that, though I don't think it's going to be matter that much in our computation. Next page. Okay, so this is really my second derivative, and let's actually analyze from here. So f double prime of x equals to 0. So this will implies me that either sine of x equals to 0 or cosine of x equals to 1. Okay, sine of x equals to 0. This is quite clear. So this will be x equals to 0, pi, and 2 pi. Okay, so cosine of x equals to 1. This means x equals 0 and 2 pi. So the solution is already included. So I don't need to worry about it. Okay, so we have got three numbers over here. So although in this case, well, the functions, the point 0 and 0, 2 pi, so these points are actually going to be the boundary of the points we are considering, but notice that they are not the boundary of the domain. So because the domain is actually a little bit larger than 0 and 2 pi. So this way, so they are still critical numbers for the second derivative in this case. Okay, finally, we have got the third point pi over here. So these 3 points separates the finite interval 0 to 2 pi into two parts, and we need to look at the sign of the function over here. But well, this is pretty easy for me to see because, well, first, if you look at the three factors, sine of x, 2 cosine of x minus 1, and moreover, finally 2 plus cosine of x to the cube. Okay, so sine of x. So sine of x is going to be positive between 0 and pi, and this will be negative between pi and 2 pi. So you can see this either by the graph of the sine function, or you could subtract the point x equals to pi over 2 or x equals to 3 pi over 2. So the first value gives you 1, the second value gives you -1. So that way you get the sign. Okay, cosine of x minus 1 is always negative. And finally, the last one, 2 plus cosine of x to the cube is always positive. All right, so this way I see that my function is concave upwards and downward respectively on these intervals. Okay, so we are now ready to sketch the graph. Let's first collect the information here. So y-intercept is 0 and x-intercept is k pi, but since we are only interested in this finite interval temporarily, so we will only mark 3 points over there. So I will just mark 0 and pi and 2 pi's. So these are the points where the function crosses the x-axis. Okay, so moreover, let's mark the other important points. So we don't have horizontal asymptotes, we don't have vertical asymptotes, and we have got 2 pi periodic. So this is why I'm leaving a space over here, so that because I need to shift this part of the graph to the left and to the right. Okay, so now other special points are 2 pi over 3 and 4 pi over 3. The white values are √3 over 3 and minus √3 over 3. Okay, so let me actually write down. So this is where 2 pi over 3 sits in, and this is going to be 4 pi over 3. So I'm moving the 4 pi over 3 on top because the function value is negative at that point. Okay, so about moreover, okay, I think I forget to actually say that f pi of equals to 0. So this is actually an inflection point. And also from periodicity, so well, the concavity will just repeat like this. So that way, I also know that f of 0 equals to 0 is also inflection point. And also f of 2 pi equals to 0. So this is again inflection point. I know the function value is close to 0 because I see that from the y-x intercepts. All right, so yeah, so that at the point, so what's the maximum, the largest possible value as we have seen, the largest possible value is √3 over 3, and the smallest is going to be minus √3 over 3. So we can actually draw it a little bit higher. So to arrange a scalar like this, so this will be √3 over 3 on top, and this is taken at the point 2 pi over 3. And for minus √3 over 3, so this is going to be like I will just mark it over here. And this is taken at the number 4 pi over 3. All right, so these will be the number, this will be the points where the function will cross. Okay, so we see that at 2 pi over 3, at the 2 pi over 3, we have got local max, but also at 2 pi over 3, so which sits in here, so the function looks concave down. So this basically tells me that local maximum looks like this. So that's telling me that, well, at 2 pi over 3, the function looks like this. Similarly, at 4 pi over 3, the function looks like this. Okay, if we want to be strict, we also should know the derivative at the point 0 to figure out, is it going to have a small slope or have got a large slope? But for this course, it doesn't really matter. So as long as we can, because we want to connect this piece with this piece over here. So I think the only reasonable way is to connect it like this. Okay, so yeah, basically, I think we have all the information we want. And now let's start the connection. So at the point 0, so starting from 0 to 2 pi over 3, the function will be increasing in a way that is concave down. So that's basically what I have over here. So this is how I will connect the first two pieces. Okay, so then the function will start decreasing after hitting 2 pi over 3, then it will be decreasing until it hits pi in a way that's concave downwards. After hitting pi, so let's move this pi outside of my trajectory. So after hitting pi, so I will just move further down in a way that is concave upwards. So let me actually draw. So this is because pi is an inflection point, so the function is decreasing, but now concavity changes. Okay, finally, well, after 4 pi over 3, and the function will be increasing up to 2 pi. So let me remove this 2 pi to somewhere that doesn't block my trajectory, so that the function will be increasing in this way. Okay, so this is how the graph looks like in one period. And to get the full diagram of the function, so all you need to do is to copy these curves to the right. So for example, this is how I get to this part. And I also need to continue a little bit to the right and show that this is concave up a little bit. Then I will also copy this part to the left. So this is basically the concatenation of these parts over here. And let me just copy again this parts to concatenate. So this way, it's quite clear that we have got a periodic function. And then you can maybe make another copy of the stuffs down here. And then, well, connect it a little bit. So prolong it a little bit to show that the pattern actually goes further, actually. So that's basically finishing the graph. And also, certainly, we should actually remove this unnecessary marks obtained from copy. Okay, so this is an example of periodic function. So we first finish discussing this part and then copy things around to finish the graph. Okay, so as you could see that if we managed only to finish this part over here, so if we started by focusing on 0 pi, then, well, using the property that the function is odd, we will just obtain this part by the fact that we have got an odd function. So this way, well, in our previous analysis, originally we have got 2 intervals for concavity and 3 intervals for the increasing decreasing. But if you focus on 0 to pi, you only have got the 1 interval for increasing for concavity and only 2 intervals for increasing decreasing. I will leave it to you to figure out that simplification. So I will not go over this part here. And okay, certainly I need to actually supplement that this is x-axis, this is y-axis, and I need to specify that the graph I'm drawing is y equals to sine of x divided by 2 plus cosine of x. All right, so this concludes the problem 40. Now let's look at problem 48. So the function we are supposed to draw is e to the x divided by x squared, and we are already given the derivative over here. So now let's actually start from scratch on each of the topic. Okay, so what should we start with? well, the first thing we should start with is the domain. Okay, so for this guy over here, so e to the x is defined everywhere. X squared, on the other hand, is on the denominator, so that x is not supposed to take 0. So this will tell me that domain is going to be minus infinity to 0, union 0 to infinity. Okay, so this is domain. Okay, what should we do the next? What should we do the next? The next thing is the intercepts. So for y-intercept, this requires me to take the value of f of 0, but the f of 0 is, well, 0 is outside the domain, so this does not apply here. Okay, for x-intercept, so this basically means I need to solve the equation e to the x equals to 0, but no solution. So this guy has got no solution, so this means the function does not really cross the x-axis, the x-axis. Okay, what should we do the next? It should be symmetry. So let's see what happens with f of minus x. So this will be f e to the minus x divided by minus x squared. Okay, so the denominator is the same, but the numerator is completely different. E to the minus x and e to the x, they have basically, they do not have much relation to each other. So then this guy does not equals to f of x or minus f of x. So, and moreover, so this guy is obviously not symmetric, not periodic. So this way we conclude that no symmetry for this one. Okay, what's the next one? The next one will be asymptotes. So because there's no symmetry, so I need to worry about two sides. Okay, so the limit at infinity for this problem is a little bit tricky. So I don't think there is an easy way for you to justify without using the L'Hopital's rule. Although there is one way to justify, I can show you that. So, well, we can use the property. So the fact is actually the following. So as x gets sufficiently large, so e to the x will be larger than x to the n for any n. So, so this basically says, well, exponential function grows faster than any polynomial function. So using this fact, I can actually get the following, that e to the x as x gets large. So e to the x will be larger than x cubed, so that e to the x divided by x squared will be larger than x, and x approaches infinity. Okay, so my function is larger than something that gets very large. So this way I will get, so this way I will be able to tell that the limit of e to the x as divided by x squared as x approaches positive infinity, this is going to be positive infinity. Okay, but this is not really a good justification because it assumes you to actually know this property, and we never really rigorously justify this property. So I think if we were going to give you a problem like this in the test, we will actually tell you that this is the limit you could use. Okay, so this is the first justification. And well, certainly you could use L'Hopital's rule twice to justify that this guy is approaching positive infinity. I will not bother to write down the details over there. Okay, so on the other hand, well, the limit at minus infinity, that one is easy. So because as x approaches minus infinity, so e to the minus x approaches to 0, and 1 over x squared approaches to 0. Sorry, it's not e to the minus, e to the x. So e to the x, namely e to the very negative number, so this is going to be, gets close to 0. So, well, then by the product law, I know that e to the x divided by x squared approaches 0. So we do have got a horizontal asymptote, y equals to 0 actually to the left. So to the left. And also we should know a little bit about this guy. So because we know that e to the x is positive, 1 over x squared also is positive. So that means both of these guys are approaching 0 from above. So as a result, the e to the x divided by x squared is also approaching 0 from above. All right, so this finishes the discussion of the horizontal asymptotes. Now let's look at the vertical asymptotes. So for vertical asymptote, it's necessary for us to discuss what's going on at the point 0. So as x approaches 0 from the right, you'll see that e to the x divided by x squared will approaches, this guy is approaching 1. Well, e to the 0 is going to be equals to 1 divided by 0, but because it's x squared, so it's always 0 from above. So this is going to be positive infinity. So moreover, as x approaches, yeah, this should be period. So moreover, as x approaches 0 from the left, the similar story, we get e to the x divided by x squared equals 2. So this will approach 1 divided by 0 from above, because x squared, again, is going to be a very small positive number. So this way I get positive infinity. All right, so this way I know that a vertical asymptote, well, the vertical asymptote is simply going to be x equals to 0. All right, so that we get a horizontal asymptote and vertical asymptote in this step. Okay, now what's next? The next will be step E and F, well, where we use the derivative to determine the increasing, decreasing intervals and the local maximum and minimum. Okay, so let's look at the derivatives. So the derivative is already computed given here. So you see that f prime of x equals to 0. So this means e to the x times x minus 2 equals to 0. But then e to the x is never 0, so you can divide it out from both sides, so that you get x equals to 2. So that will be one solution, one critical number. And f prime of x does not exist, so this means the denominator equals to 0, but the denominator equals to x. So this tells me that x equals to 0. All right, but x equals to 0, this is outside the domain. So we do not need to worry about it too much. So though we still need to actually keep it on the number line when we perform the analysis. All right, so these are my critical numbers. And now let me draw the number line. So, well, so I have got the number 2 with the solid dot, and I've got the number 0 with the hollow dot. All right, so these two numbers separates the real line into two parts, and I need to analyze the increasing and decreasing on both sides. Okay, so we basically have got three factors. So namely e to the x, x minus 2, and finally x cubed. Okay, e to the x is always positive. X minus 2 is positive to the right of 2 and then negative to the left. And finally, x cubed is positive to the right of 0 and negative to the left of 0. So that way I know my function will be increasing, decreasing, and increasing. Okay, so this is going to be the intervals of increasing and decreasing. And moreover, let me actually move this down a little bit because I want to mark my function value at 0. Okay, my function does not really take a 0 at the point, so that means I don't need to worry about this guy over here. All I need to worry about the function value at the number 2. So f of 2 is going to be equals to e squared divided by 2 squared. That will be 1/4 e squared. Let me just pick it like this. So this will be a number that's going to be a little bit larger than 1 because e is greater than 2. So it's 2.7 divided by 2. This is basically going to 1.3. And 1.3 squared, this will be less than, yeah, this will be less than 1.9, but greater than 1.7. So basically speaking, this is going to be a little bit less than 2. So this number will be. Okay, so no matter what, we get f of 2 equals to 1/4 e squared. So this is going to be local mean. All right, so this is basically what we know from the first derivative. Now let's look at the second derivative. So the second derivative looks like the following. So let me just perform step G for concavity analysis. So let me copy my f double prime from the previous slide. So that will be e to the x, x squared minus 4x plus 6 divided by x to the 4th. Okay, so this one is pretty easy because if you look at f double prime of x equals to 0, so that basically means x squared minus 4x plus 6 equals to 0. So you don't need to worry about e to the x. But x squared plus 4x plus 6, if you look at the discriminant, so you can either look at the discriminant of this quadratic equation, or you can simply write it as x minus 2 squared plus 2 equals to 0. So this is simply completion by square. So well, you see that x minus 2 squared is supposed to be equals to minus 2, and then this tells me that there's no solution because the left-hand side is always positive. So that's why there's no solution for this guy. Okay, so f double prime of x does not exist. this will simply tell me x equals to 0. So for the second derivative, the situation is easier. So I only have got one number, and that number is actually, again, outside of domain. Yeah, I forgot to say that. So I only have got one separation, and I don't need to worry about the function value no matter what. And then all I need to worry is basically the graph. But then it's quite clear that from here that e to the x is going to be always positive, and then x squared minus 4x plus 6. Well, we have already obtained this expression, so we know that this guy is also going to be always positive. And finally, x to the fourth in the denominator, this is always positive. So this way, we know that the function is concave upward everywhere. And in particular, there's no inflection points. So this finishes the analysis of concavity. Yeah, I forgot to say over here. Okay, so now we are ready to draw the graphs. Let's see what we have. So no intercepts, and then no symmetry, and then, okay, we have a bunch of limits. So to the right, well, the function gets large, and to the left, the function gets close to 0. All right, so moreover, to the left, the function is going to be 0 from above. So at least I know that my function will look like this near the point 0. So moreover, we have got a vertical asymptote at x equals to 0. So well, and moreover, the limits are all positive infinity on both sides. So this tells me that, well, the function will look like this and this, well, to the left and to the right of 0. And finally, I have got f of 2. So f of 2 is going to be a number that's going to be smaller than 2. So that, let me mark it over here. So this will be a number 2, and this will be, let's say, yeah, because this is smaller than 2, so I'm actually drawing this way. So I would say this is precisely my 1/4 e squared. So that this not point, yeah, I better move it a little bit to the right. So that this point will be the point it passes through. Moreover, I know that the function takes the local minimum at 2, and the function is concave upward at this point. So this tells me that my function will have to look like this way. Okay, finally, to the very right, so we have concluded that the limit is going to be infinity. So this way means it's going up to infinity. Now we are ready to connect the bits. So we know that the function is increasing in a way that's concave upwards at x less than 0. So this way we can make the connection like this. Okay, so I can actually get rid of this part and make it look a little bit nicer. Okay, so to the right of 0, the function becomes decreasing until it hits 2, and in a way that's concave upwards. So that's basically how I get to this part. Okay, finally, to the right of 2, the function becomes increasing and all the way up to infinity. So this is how I connect these parts. Okay, yeah, sometimes when you draw the preliminary sketch, and you will find that, well, the preliminary sketch is a little bit ugly and it refuses to connect. So, well, some kind of modification is necessary. Okay, so this will be the graph for my current function, and let me actually supplement it. So this will be my x-axis, and this will be my y-axis. And the function I'm drawing in this problem is going to be y equals to e to the x divided by x squared. All right, so this finishes the problem 48. Okay, we will conclude this supplementary video by the last example that involves a logarithmic function. So we are asked to draw the graph for the function natural log of sine of x. And let's see how we should proceed. So again, what do we start with? We should start with the domain. Okay, so what's the domain over here? So in order to make sense of any logarithmics, you need to make sure that the argument is strictly positive. So that means you need to make sure the sine of x is strictly greater than 0. Okay, how do we solve this inequality? So you need to look at the graph of the sine function, and I will draw it in green over here. So the graph of the sine function basically looks like it will be positive from 0 to pi, negative from 0 to pi to 2 pi, and then positive from 2 pi to 3 pi, negative from 3 pi to 4 pi, etc. So then this pattern repeats, well, negative from negative pi to 0 and positive from negative 2 pi to pi. So from the graph of the sine function, we see that the sine function is positive when x is sitting between 0 to pi, 2 pi to 3 pi, and then 4 pi to 5 pi, etc. And also we may have got, well, minus 2 pi to minus pi, and then minus 4 pi to minus 3 pi, well, etc. So you see that there are lots of intervals union together. So this looks very complicated, but we should not be worrying about this too much because, well, we will soon discover that this function is periodic. So once we know that this function is periodic, all we need to do is to focus on one of these intervals. All right, but let's discuss that later. Okay, so this is a domain. What's next? Okay, the next thing should be the intercepts. Okay, so let's actually start from the y-intercepts. So for y-intercept equals to f of 0, which is going to be natural log of sine of 0, but this guy, you know that this is undefined. So this way we see that no y-intercepts. Okay, so on the other hand, for x-intercept, as we have seen, well, there will probably be a lot of intercepts. So then you need to solve the equation natural log of sine of x equals to 0. Okay, a word of caution is actually this does not really imply that sine of x equals to 0. Instead, you should actually recognize that 0 is indeed natural log of 1. So natural log of sine of x equals to 0. So this will imply that sine of x equals to 1. And that way you will get a bunch of solutions, x equals to pi over 2, and then 5 pi over 2 pi plus pi over 2, and 4 pi plus pi over 2, and then you may have got plus and minus signs over here, etc. So you will have got infinitely many intercepts for this function. But again, since we are working with the periodicity, so we do not need to worry about that infinitely many points at the end of the day. Okay, so what should we study the next? Well, you should recall the next thing we want to study is precisely the symmetry. Okay, so regarding this one over here, I will not bother to actually write what the f of minus x is, but then we can see directly that this function is neither even nor odd, because you should notice one thing, that for functions that are even or odd, so their domain has to be symmetric about the point 0. But well, if you look at the domain for this guy over here, so 0 pi, 2 pi to 3 pi, and minus 2 pi minus pi. So this is not symmetric about the point 0. So this is, so let me just write the reason. So because the domain is not symmetric about x equals to 0. So there's no need for me to actually consider what f of minus x is. Okay, but on the other hand, we do have another type of symmetry, namely the periodicity. So f of x plus 2 pi, so this is simply going to natural log of sine of x plus 2 pi. And well, sine of x plus 2 pi is simply sine of x, so that way we conclude that f of x plus 2 pi equals to f of x. So this tells me that the function is 2 pi periodic. And precisely because of that, so we can focus on 0 pi. So we know that this function is periodic over 0 to 2 pi, but because it's only taking up half of the part, so we can simply focus on one of this part over here. Okay, so this is the interval we want to focus on, and it's precisely because of that when we discuss the asymptotes. So the horizontal asymptote is not applicable over here. But on the other hand, when we try to discuss the vertical asymptote, so we should notice the following. So we should first recall that the limit of natural log of u as u approaches 0 from above. So this guy is indeed going to be minus infinity. So because the graph of natural log of x looks like this. So as x gets close to 0, the function blows down to minus infinity. So, well, with this in mind, let's investigate what happens to the endpoints of the domain. Okay, so as x approaches 0 from the right, So you see from the graph of the sine function, if x approaches to 0 from the right, sine of x will also approach 0. And you should know that sine of x is approaching 0 from above. So because sine of x is approaching 0 from above, so natural log of sine of x as x approaches 0 from above, so this will be approaching minus infinity. Okay, so this is what happens at the endpoint. And at another endpoint, as x approaches to pi from below, you should also conclude from the picture of the graph of sine of x, while x gets close to pi, sine of x is also getting close to 0 and it's from above. So as a result, we also conclude that natural log of sine of x is approaching minus infinity. All right, so this basically tells me that I have got two vertical asymptotes, x equals to 0 and x equals to pi. That finishes our discussion of the asymptotes. Now let's study the intervals of increasing and decreasing and local maximum and minimum. So you need to figure out where f prime of x equals to 0, but f prime of x equals to cosine of x over sine x. So this will tell me that cosine of x equals to 0. So over 0 to pi, well, there's only one number that makes cosine 0. So namely x equals to pi over 2. Okay, so on the other hand, if f prime of x does not exist, this means sine of x equals to 0. Okay, but in our domain, sine of x is supposed to be greater than 0. So this way we get no solution. Okay, so this means all I need to worry about is one single critical number, pi over 2. And this critical number separates the open interval 0 to 2 pi, 0 to pi actually, 0 to pi into two parts. Okay, so to determine the sign is pretty easy. So the numerator is cosine and the denominator is sine. And we know that sine is always positive because that's our requirement of the domain. And cosine of x, well, it will be positive for an angle that's less than pi over 2, and it will be negative for an angle that's greater than pi over 2. Okay, so this way I know that the function will be increasing from 0 to pi over 2 and decreasing from pi over 2 to pi. So also this makes the function value at pi over 2 special. So f of pi over 2, so this is going to be natural log of sine of pi over 2, and this is precisely natural log of 1. You should recall that natural log of 1 equals to 0. Okay, so this basically tells me that my function takes the value 0 f pi over 2, and this 0 is a local max. All right, so this finishes the step E and step F. Finally, we study the concavity. So recall that f double prime of x, well, this is simply going to be the derivative of the cotangent function, and we know that this is going to be minus 1 over sine square x. Okay, so this is pretty easy because f double prime equals to 0. So this has got no solution. Well, the numerator is never 0, and f double prime does not exist. So this is again no solution because, well, this means sine of x has to be equals to 0, but sine of x is not supposed to take 0 over there. So this way, well, the interval is simply going to be not separated. So the concavity will stay the same. And also from this expression over here, so it will be 1 divided by a positive number together with negative sign. So that way I conclude, well, the function will be concave downward from 0 to pi. Okay, now we are ready to draw the graph. So because we have got a periodic function, it's 2 pi periodic, but then the domain is going to be 0 to pi and then 2 pi to 3 pi. I think for the graph, I think for the periodic function, we should show at least like 3 periods. So this means, okay, so at the right endpoint of my graph will be like, this guy will be 3 pi, and then there's 2 pi, and then pi 0. And so basically my my x-axis should range between x equals to minus 2 pi to x equals to 3 pi. So I need to move my y-axis a little bit to the left. So then, moreover, I would like to have this guy to be minus 2 pi, so that this guy will be minus pi, and then correspondingly, I can mark the pi over here. So this will be my pi, and this will be 2 pi, and this will be 3 pi. Okay, so for the 4 pi over here, I can mark it over this. All right, so these are the points I want to mark. We will first draw the graph from 0 to pi, and then we will just copy it to 2 pi to 3 pi and minus 2 pi minus 3 pi. So this will be sufficient for us to show that we have got a periodic function. Okay, let's look at the other informations. So we have y-intercept undefined, and x-intercept will be pi over 2. And together with these numbers, so this means I know my function will pass through pi over 2, and then 2 pi plus pi over 2, and minus 2 pi plus pi over 2. So these are the points that the function will pass through. Okay, so from the next section, I have know that it's going to be periodic function, neither even nor odd, and no horizontal asymptote, and vertical asymptote will be x equals to 0, x equals pi. So at least I need to draw the vertical asymptote over here. We also know the limit to the right of 0 will be minus infinity, and to the left of pi, this will be minus infinity as well. So this will be what happens to these two pieces of the graph. Okay, so this is what we know from the asymptote. Okay, we know we have got a special point f pi over 2 equals to 0. We already plot that point on the graph, and we know that the function will be increasing and decreasing before and after. And we know the function will be concave downward at this local maximum. So this basically means, well, the function will look like this, basically speaking, near the point pi over 2. Okay, so what else do we need? Well, we basically have everything, so we can simply connect these pieces. Okay, so we already know this part, so let me actually draw. So what we have is a function that's increasing from minus infinity in a way that is concave downwards until it hits the point pi over 2, well, at the x-axis. Then it will start to be decreasing after that point, and then in a way that is again concave downwards down to minus infinity. All right, and my point over here is going to be pi over 2. Okay, so this will be the graph I have drawn for this part of the curve. And then in order to, then, well, I need to shift it, or actually copy it to the other parts. Yep, like this, and like this. And I should actually get rid of this part and supplement my vertical asymptotes. So 2 pi and 3 pi will also be my vertical asymptotes, and minus pi and minus 2 pi will again be my vertical asymptotes. All right, so then finally supplementing the x-axis and y-axis. So this is my x, this is my y, and then finally marking that what I'm drawing. So I'm drawing y equals to natural log of sine of x. Okay, so this finishes the last problem of the exercise set. Okay, so this concludes the video on exercise 13. In case you need more examples, please go to the textbook and try those problems with an odd number. So the solution manual contains the solution and together with the graphs to those functions.